Thank you for the introduction, and I would also like to thank my co-authors, Andrea, Alvaro, and my advisor, Dr. Hans-Peter Schaub. So we've seen a similar talk earlier this morning from Alvaro about measuring potentials of nearby objects in space, but he focused on one of the methods that is based on secondary electrons and photoelectrons, and this talk is focused on the X-ray method. Next slide. So Alvaro talked earlier about the motivation of the sensing method. So initially, the main motivation was the electrostatic tractor. So the electrostatic tractor is an active debris removal method for geostationary debris, where you have a servicing satellite equipped with an electron gun, and that electron gun is aimed at the retired satellite or the debris, and therefore you create a positive charge on the servicing satellite and a negative charge on the target object, on the debris, and that results in an electrostatic attractive force that you can use to tug the debris to a graveyard orbit. And the relative motion control for this method is really sensitive to estimation errors of the electric potential. So you really need to know or have a good approximation about the electric potential of both spacecraft. And this is really what motivated the study on how to remotely sense electric potentials. And some more recent work also focused on electrostatic perturbations. If you have an uncooperative target that you want to dock with for servicing operations or so, and you're in the charging environment and the two spacecraft are charged, then this can significantly perturb your relative motion and lead to tumbling rates on the target object that you need to match with the servicing satellite. And all this takes advantage of remotely sensing electric potentials. Next slide. So Alvaro talked about what we refer to as the electron method. The second method that I'm going to talk about is the X-ray method. So on the servicing satellite, you have an electron gun that is aimed at the target object. And the electrons from the electron beam interact with the environment if the two spacecraft are charged or if one of them is charged. So if you have an initial energy of, let's say, 10 keV on the electron beam, that electron or those electrons are being slowed down as they approach the target object if the target object is charged negatively, and they're accelerated towards the target object if the target is charged positively. And the difference, for example, if it's charged negatively, the loss in kinetic energy of those electrons corresponds to the difference in electric potentials between the two spacecraft. So the question is, if we know the initial energy of the electrons from the electron beam, if we could estimate or find out what the landing energy is of those electrons at the target object, then we could compute the difference in potential between the two spacecraft. So if we know the potential of the own spacecraft, the servicing spacecraft, we can infer the potential of the target object. Now the question is, how do we find out what the landing energy is of those electrons? And that's where the X-rays come in. So on the top right, you see some sample X-ray spectra. There's a characteristic radiation peak at 1.5 keV. That's the characteristic radiation for aluminum. And the other part is the continuous spectrum. It's called the Bremsstrahlung spectrum. And those X-rays are only emitted to an energy up to the landing energy of those electrons. So if the spectrum, for example, the blue one ends at 6.5 keV, that means that those electrons from the electron beam had a landing energy of about 6.5 keV. So by finding that maximum energy in the X-ray spectrum, we can estimate the landing energy of the electrons and therefore the potential of the target object. Next slide. So we ran a few experiments with complex shapes, which makes interactions with the electron beam a lot more interesting. So our setup was in a vacuum chamber with an electron beam coming from the top left in the top picture, and a target object in the bottom right corner of that top picture, consisting of a panel, or like a spacecraft panel, and a spacecraft bus, or like the cube. So we have two components that we can charge different potentials to simulate or to have differential charging, and the shape of the object is pretty complex as well. We have a phosphor screen attached to the backside of the cube. That way, if we reorient the target object, we can verify where the beam lands for one orientation, and also like verify the spot size of the beam on the target object. And we have a stepper motor connected to that target object, so we can change the orientation and all that. And we use an X-ray detector to detect those X-rays. And for numerical validation, we use Simion to verify or find out where the beam approximately hits the spacecraft. That's really helpful for those experiments with complex shapes. Next slide, please. So this is a slide from an earlier presentation at SciTech this year, where we also looked at how does the beam interact and how can we measure potentials of complex shaped target objects. So on the bottom right, you see several sample X-ray spectra. And for the first one, let's look at the blue one. We see two characteristic peaks at 5.5 and 6.5 keV. So that these peaks correspond to iron and chromium. So that tells us that we are hitting some object with steel. And we used a electron beam energy of 10 keV for this experiment. And the estimated landing energy of that blue line is about 10 keV. So basically, we're measuring a 0-volt potential. Now, these two factors combined, the material steel and the 0-volt, basically tells us that we are not hitting the target object, the aluminum spacecraft, with our beam. We're actually hitting the chamber wall, and that's confirmed by the numerical simulations on the top. For for an orientation of negative 20 degrees, the beam is actually deflected so much that the beam is actually hitting the chamber wall, and we're estimating the potential of the chamber wall. And yeah, by the way, so the orientation of the spacecraft is defined as 0 degrees would correspond to the panel aligning with the electron beam. Now, for 30 degrees, for an orientation of 30 degrees, that corresponds to the yellow line, we see a characteristic peak of 1.5 keV. So that tells us we're actually hitting the target object, the aluminum target object, with our electron beam. And we have an estimated landing energy of about 8.5 keV. So for a beam energy initially of 10 keV, that corresponds to a potential of negative 1.5 kilovolts. And that corresponds to the potential of the spacecraft panel in this case. And then again, for another orientation, for 80 degrees corresponding to the purple line, we have an estimated landing energy of 9.5 keV, corresponding to the bus potential of negative 500 volts. But really what this highlights is that it really depends on the orientation of the spacecraft, where the beam will land, and therefore which potential we're estimating. And also at the same time, these X-ray experiments, they usually use so far we have used a 20-second measurement period. So for 20 seconds, the X-ray detector is counting X-rays. Now that also means that for 20 seconds, we need to hit the same component of the spacecraft, which is pretty unrealistic maybe in a space scenario. So the question is, what happens if the beam is hitting multiple components during those 20 seconds? Does this interfere with our measurements, and can we actually measure both potentials of both components at the same time with one spectrum? So next slide, please. So for that, we have to think about how does actually a X-ray spectrum, how does it look like if it comes from two different sources, from two components charged to two different potentials. So let's say we have a 10 keV electron beam and two components, one with 0 volts and one with negative 3000 volts. Well, the X-ray spectrum from the first component is the one on the top left, which has a maximum landing energy, or has a maximum energy in the spectrum of 10 keV. And now the second individual spectrum would have a landing energy or a maximum energy of 7 keV. And the total spectrum would be a superposition of these two individual spectrum as seen on the top right. And where the at 7 keV, where we basically have the second potential, there's a little bump in that total spectrum. So if we could find this little bump or this little deflection point, then we could estimate the potential of not just the first component, which has a landing energy of 10 keV, but also the second one. The problem is, as we saw on the earlier slide, the spectrum has quite some noise in there. So we will not be able to find the change in like this deflection point or this bump. So our approach is actually to estimate the potential of the first component first, the one with the landing energy of 10 keV. Using that landing energy, we compute a theoretical spectrum using X-ray Bremsstrahlung models. And then we subtract that theoretical spectrum from the actual measured spectrum, which leaves us with a residual spectrum, which would correspond to the individual spectrum created by that second component with the other potential. And earlier, we did experiments with a really wide electron beam that hopefully impacts two components at the same time. But first of all, these experiments were pretty challenging because it is hard to find the perfect orientation of the target object such that the beam actually impacts both components at the same time. And second, it's also pretty unrealistic in a space environment where the target object might be rotating, tumbling. It will be really hard to aim the beam in a way that it perfectly hits that spot between two components. So so we changed our experiments to dynamic experiments, where we have a rotating target object. The target object is rotating for 20 seconds. And during those 20 seconds, we're counting X-rays with our X-ray detector. Next slide, please. Yeah, so next. So for a orientation of 60 degrees, for example, if we start here, this is where our experiment starts. The electron beam will hit, according to the numerical simulations, the electron beam will impact on the spacecraft panel. But then next, as the orientation of the target object of the spacecraft shape primitive changes, the landing location of the electron beam changes as well. Next. And next. And at some point, the electron beam actually impacts the cube. So if we rotate it by 30 degrees, that's what we did in our experiments. We rotate over 30 degrees within 20 seconds. And if we're counting X-rays during that time, the total measured spectrum in the end will include information from both the panel and the cube if the electron beam impacts both components during that time. Next. So here I'm just showing some sample X-ray spectra. So this one on this slide is for a rotation between 20 and 50 degrees. And the spacecraft bus is charged to negative 3,000 volts and the panel to negative 1,000 volts. And the object is, during those 20 seconds, it sweeps from 20 degrees to 50 degrees. So on the left hand, on the left slide, or on the left side, sorry, we see the measured spectrum after 20 seconds. There we have an estimated landing energy of about 9 keV, which corresponds to the potential of the panel of 1 keV for a 10 keV electron beam. Using that landing energy, we compute the theoretical spectrum, that's the red line. And as we can see, that red line fits the measured spectrum really, really well, actually, which tells us that there is only one potential. There is only the potential of that panel. And that's confirmed by looking at the right-hand side at the residual spectrum. So the difference between the measured spectrum and the theoretical one, it's basically just noise. It doesn't look like an actual Bremsstrahlung spectrum. It's really just noise. So it's very low in intensity. So in this case, we're actually just detecting the potential of the spacecraft panel. Next slide, please. Now, this sample spectrum here is for a rotation between 80 and 110 degrees. So here the electron beam actually switches or goes from one component to the other, somewhere in between those two orientations. So again, using the measured spectrum, we estimate the landing energy, compute a theoretical spectrum, the red line, and now these two spectra actually deviate from each other. They're pretty different. So if we take the difference of those two, we actually, and that's shown on the right side, we actually have a residual spectrum that is pretty high in intensity, and it has the shape of another Bremsstrahlung spectrum. So this is really like an individual spectrum from that second component, and using that spectrum, we can estimate the potential of the second target, which is corresponds to a landing energy about 7 keV or 3,000 volts potential on the bus component. So in this case, we actually detect both the bus and the panel potential. Now, there is two things I should mention about that theoretical spectrum. So one of the challenges is knowing the intensity of the theoretical spectrum. Like we get the measured spectrum, and we know kind of how far away is the source location of those X-rays. But coming up with a theoretical intensity, or with the right intensity for that theoretical spectrum, is pretty hard. In theory, it's easy to compute. It's just it depends on a bunch of parameters that we don't really know. So what we did here is we fitted the intensity of that theoretical spectrum to the actual measured spectrum for the last 1.5 keV. So if there's an estimated landing energy of 9 keV, we use the range between 7.5 and 9 keV to fit the intensity of that theoretical spectrum to match the actual measured spectrum. And that's kind of necessary to work with the residual spectrum and all that. But the problem with that is that it also essentially limits how small of a potential difference we can measure. If we fit that curve, or the intensity of the theoretical spectrum, for an energy range of 1.5 keV, then that means that we can only detect potential difference larger than 1.5 keV. And the second part is that this theoretical spectrum is highly dependent on the material of the target object. So if those two components were made out of a different material, we would run into problems with using that theoretical spectrum and working with the residual spectrum. Next slide. So here are some experimental results for two different configurations with potential. So the white points correspond to the first estimation, which corresponds to like the maximum energy in the spectrum. That will always measure the potential of the panel in our experiments, because that's the potential that has the higher landing energy. And then the blue markers indicate what we measure, the potential we measure with the residual spectrum, so the second estimation. And it works somewhat well. The errors are larger compared to the first estimation, just because the residual spectrum is usually lower in intensity. That means we have a not such a good signal to noise ratio, so it makes the estimation a little harder. And we can also see that for those lower angles, we have larger errors. And that's also because we need to find a good way of rejecting residual spectrum when they're not, when they don't have a sufficient intensity, basically. Like if you work with the residual spectrum is very low in intensity, it's basically just noise. It doesn't really have any Bremsstrahlung spectrum in there. So any potential that you're trying to estimate with it is going to be really large in error. That's why those estimations to the left are usually with higher errors. Next slide. So yeah, in conclusion, we found a way of measuring multiple or estimating multiple potentials simultaneously, and that's pretty promising for tumbling spacecraft or tumbling target objects, where the landing spot of the electron beam really changes over time. But the problems we were running into is and I'm really looking forward to maybe some suggestions about how to deal with this. The problems are really when do you reject a residual spectrum when it's too low in intensity, because that will give you really large errors if you don't reject those bad signals, basically. Second part is, the second challenge is the fitting the intensity of the theoretical spectrum to match the intensity of the actually measured spectrum. And the last challenge is really, and that's what we're going to look at in the future, is doing experiments with maybe 3 components with 3 different potentials, and especially with different materials. Maybe one component is made of aluminum and the other of steel, and so on. This should be really interesting, but definitely necessary to investigate. Yeah, so next slide, please. With that, I'll be happy to answer any questions.